I'm Shigang Chen, a professor from University of Florida. Our paper is Generalized Sketch Families for Network Traffic Measurement. In the zettabyte era, there's a lot of network traffic flowing through today's internet every day. If we can measure such traffic, we can do a lot of things, such as anomaly detection, network access profiling, traffic control, accounting, billing, and network security functions. So in this paper, we model network data as a set of flows. Each flow is uniquely identified by its flow ID. For example, per source flow, its flow ID is the source address in the packet header. And by using a combination of different header fields, we can define flows under measurement flexibly. So this example, packet, from a router's point of view, the arrival packets are abstracted as a sequence of FE pairs, where F is the flow ID and E is the element under measurement, which is defined by the user. In this example, you have a sequence of packet P1, P2, P3, P4, and so on, arriving at a router. And they are abstracted into flow ID and element pair, F1, E1, F2, E2, F3, E3, and so on. So there are two types of measurement. One is called flow size, which is to measure the number of elements in the flow. Essentially, it's the number of packets in the flow. The other is flow spread, the number of distinct elements in the flow. So this is a harder problem than flow size because you have to remember the elements you have seen so far in order to find the duplicates and not count those duplicates. Now, in the above example, we can imagine that the flow ID can be the source address, and the element under measurement can be the destination address. Both of them are in packet header. So flow size is the number of packets again. So let's say flow F1, you have 3 packets, P1, P4, P5, F2 have 2, P2, and P6. The flow spread is the distinct number of destination address that each source has contacted. This can be used in scan detection, right? You profile how many destination address that each source has contacted. If you contact too many, you're a scanner. So in this particular example, flow source address F1 send all its 3 packets to the same destination address E1. So its spread is 1. For F2, it has 2 packets, but they are sent to different destination address E2 and E4. So its spread is 2. Now in reality, there are flows that has millions of distinct elements, distinct destination address, for example, or have even billions of distinct elements. In that case, it takes a lot of memory to remember what you have seen, right? So it can be very costly for flow spread measurement. So we have 3 requirements for our solution. One is we want to support per flow measurement for both flow size and flow spread. We want our solution to be general. With a plug-in design, you can plug in different data structures for different measurement function and different performance accuracy trade-off. We also want our solution to be to have low space and processing overhead. For low space overhead, we want the overhead to be down to a few bits per flow on average, which is very challenging. Think about the spread measurement. And we want the processing overhead to be down to 1 memory update per packet with a couple of hashes. There will be more expensive algorithms, but in our solution framework, but it's a trade-off. Some are less accurate, but more efficient. So to proceed with our proposal solution, we first review counting broom filter, which serve as a basis. So its data structure is a single array of counters. And for each arrival packet, FE will hash the flow label, flow ID, to D counters. In this example, D is equal to 2. For example, F1 is hashed to 2 counters, and those 2 counters will be increased by 1. And F2 is hashed to 2 other counters. Well, they actually share 1 counter. And these are the 2 more packets come in, and each of them cause 2 counters to be increased by 1. When we query for the flow, this can only do flow size because the counter cannot remember the elements that we've seen so far. So to query for the flow size of flow F, we'll hash F to D counters and take the minimum value of those counters. And we generalize this to a family of Bloom sketches by replacing each counter with a plugin, which is an estimator data structure. So the counter array is replaced by an estimator array, and each plugin estimator consists of 1 or multiple unit sketches. And those unit sketches can be any data structure you choose. By using different estimator types, we can measure flow size, spread, and other statistics. And as the figure shows, 2 flows may be hashed to the same estimator in the array. Therefore, they share the same estimator. But by taking the minimal value of the D estimators for each flow, we can minimize the noise introduced by other flows. In the table below, you can see that if we choose estimator to be counter, then that's counting Bloomfield. It can be used for flow size measurement. In our framework, we refer to it as bSketch counter. And the estimator can be bitmap, FM sketch, hyperlog sketch. And they can be used to measure both flow spread and size. And the estimator can be a composite one. For example, bSketch counter and hyperlog. Each estimator contains a counter and a hyperlog estimator. They can be used to measure flow size and the flow spread simultaneously. Another example is bSketch, bitmap, and hyperlog. Bitmap is good at to give accurate estimation for flows of a small spread, and hyperlog has the advantage of have large estimation range. By putting them together, we can achieve both accuracy for the small flows and the large estimation range. The next solution is a family of virtual sketches. So here, instead of using an array of estimators, we use M arrays of unit sketches. So here, the physical data structure is M array. Each consists of W unit sketches, which can be counter or bit or register, which is used in other type of sketches. For each flow, we construct a logical estimator, okay, by drawing 1 unit sketch from each array, so through hashing. And every flow is pseudo-randomly pick 1 unit sketch from each array to form its logical estimator. And the 2 flows may share a common unit sketch due to hash collision. So when we try to record a packet FE, we're going to hash this packet to 1 unit sketch in the logical estimator of the flow. And that unit sketch is taken from the physical array. So the actual recording happens there. Because 2 flows may share a unit sketch, so they will record the information to the same place. and that introduce noise to each other, and we have to remove the noise when we estimate the size and the spread of these two flows. So the idea is that during the query phase, we're going to make an estimation based on the logical estimator. And it contains the flows elements, say it's K elements, and also contains some elements from other flows due to unit sketch sharing. So let's say X is the total elements of all flows. X minus K is the number of elements from other flows. And these elements each have a chance of getting into these unit sketches due to sharing. And because we draw the unit sketches for each logical estimator pseudo-randomly, so the chance are all equal. So we can easily derive such a formula where the expected value of that derived from this estimator is equal to K plus the noise, the average noise. That can land it here. And we turn this formula into an estimator. So by using different unit sketches, for example, counter, bit, FM register, hyperlogical register, we'll have different member virtual sketches in the family, and they each perform different measurement functions. And we mathematically analyzed the estimation accuracy of these sketches by deriving the bias and the variance. And the proposed bSketch and vSketch can be used to support network-wide measurement, where measurement function happens at many routers. And these routers will send their recording to a controller where the recording will be combined to support network-wide measurement. So it contains two phases. One is online measurement that happens at each router. And periodically, the router will send its recorded sketches to a controller where the query will be made. The experiments. The traffic trace we use are downloaded from KIDA. Each trace contains 1 minute of network traffic. And we implement the proposed sketches on 4 platforms. One is OpenVSketch. The other is a standalone software implementation using a CPU or on the GPU platform. And the hardware implementation based on FPGA. The experiment metrics we use include the online recording throughput in millions of packets per second, and the offline query speed in millions of queries per second, and the memory space used by these sketches, and estimation accuracy. K is the actual flow size. K hat denotes the estimated flow size. The accuracy is defined in 3 submatrix: absolute error, relative bias, relative standard error. So first, let's see the throughput comparison under OBS. We can see that each family, different members, they achieve similar throughput. And vSketch, its throughput is slightly higher than bSketch for flow size measurement. And the reason for this is that the bottleneck within OVS is not a measurement function, it's on other modules. So these throughput actually is mostly determined by the throughput of other modules. Now, standalone implementation on CPU without OBS. And we see that the throughput is higher, and vSketch has higher throughput than bSketch because it's low overhead per packet. Next is GPU. GPU turns the tens of Mbps on the CPU to hundreds of Mbps due to its multi-core acceleration. And still, vSketch family performs better than bSketch family. Hardware implementation, our FPGA is a modest, it's not a powerful one. But we can see that vSketch, different families in vSketch or bSketch, they achieve similar throughput due to pipelining. But vSketch achieves higher throughput than bSketch. Comparison with prior art in terms of throughput. So we compare with Elastic Sketch, Unimon, and we can see that the proposed algorithm achieves a lot higher throughput than these two prior works. Query speed. For flow size, the bSketch has a lot higher, query throughput than vSketch, because vSketch, the computation overhead for estimation, offline estimation, based on the sketches that are recorded online, is higher. And the next, we compare estimation accuracy with prior art. We compare vSketch with the prior art CSE, VPCSA, vHyperlog. We can see that they achieve similar accuracy for bitmap, but using other estimators. The proposed algorithm vSketch achieves a lot smaller error than the prior art. And that's the end of my presentation. Thank you.